Okay, hi everyone. I'm Jordan Holland. I'm a third-year PhD candidate from Princeton University. Really excited to talk to everyone today about this project named nPrint, which is this idea of standardizing a lot of network traffic analysis problems through a standard packet representation. This is work done with my co-author Paul Schmidt and my advisors Nick Feemster and Pratik Mittal. We do have a website up and running with tutorials on how to use the tool. And of course, I'm available for questions as well about it. A quick overview of where we're heading in this talk. What we're going to do is we're going to introduce nPrint, which is a standard data representation that's meant to be used to solve a class of network traffic analysis problems. And we're going to use nPrint to remove human-driven feature engineering, this tedious step from the typical machine learning workflow for an entire class and set of network traffic analysis problems. And we're actually going to show equivalent or better performance than hand-engineered features on the same tasks, such as active device fingerprinting comparing with Nmap. We actually, in the paper, we do 8 different case studies, which is available on the website. We compare to POF, Nmap, and other popular tools. So a little bit of background and motivation. So at the intersection of machine learning and networking, there are really an endless amount of sort of applications of machine learning to network traffic. Some we're going to look at today include device fingerprinting, application identification. Others include, OS detection, website fingerprinting. So can I fingerprint the website you're going to based off of just your traffic pattern? We have protocol fingerprinting. Like I said, really, this is such a large intersection that there's so many use cases for machine learning and applying machine learning to network traffic that if we can do it in an easy way, we may enable rapid innovation in this space. So speaking of machine learning applied to network traffic, there's a real classic sort of workflow when you're doing when you're taking network traffic and you want to apply machine learning to it. First, you're going to hypothesize some problem. Say I want to fingerprint devices remotely, right? And then I'm going to gather network traffic that corresponds to that problem. So I'm going to probe devices in this case for device fingerprinting, and I'm going to look at the responses as my traffic. And then I'm going to look at the traffic, and I'm going to say, okay, what parts of this traffic are important to be able to distinguish different devices remotely? So, like for example, the TTL we know is important for distinguishing remote devices. And we're going to use our domain expertise and really our time to hand engineer and extract features that are hopefully predictive of that task. And then we're going to train a model on those features we've extracted. And hopefully it does well, but really this goes back and forth. So we're going to take the performance of our model and say, oh, we could probably do better. And we're going to hand engineer more features, and then we're going to train another model. And we're going to continue doing this until we're satisfied with the model's performance. What we noticed was really that the bulk of the time was spent extracting these features that are hopefully predictive of the task, right? So it takes domain expertise and really just a ton of iterations of time to figure out, what parts of network packets are important for active device fingerprinting, and then when we move to another problem, we sort of have to reinvent the wheel and say, okay, well, these features or these parts of the packets were important for device fingerprinting, but now we need entirely new features for identifying applications, right? So really this step takes the bulk of the time, and we have to redo it every time we want to solve a new problem. So our goal is to remove this process entirely, right? So we're going to take some inspiration. And our inspiration is this idea that deep learning techniques have been beyond, popularized beyond belief for a plethora of problems, but they tend to perform really well on problems related to image classification. And one of the reasons for this is that this rapid innovation is that pictures, right, have this standard representation of values, right? Whenever I want to classify a set of images, say a cat versus a dog, I present a deep learning classifier with a square or rectangle of pixels, and it's going to learn how to classify between the cat and the dog. We don't actually have to tell it how to do it. And then if I want to do, say, a boat versus a car, right? I just take the pixels once again that are the images and allow the deep neural network to actually extract the features, right? We don't have to tell the classifier that, there's the boat doesn't have wheels, right? But it extracts these on its own. So we want to see if we can do something like this with network traffic, where we can, avoid all this hard work. And then related work shows that deep learning techniques have been super effective in website fingerprinting for Tor. And this is the idea, right, that we can fingerprint the website someone is going to by just looking at the directions of the traffic, because in Tor, right, we have cells and everything is the same size, and essentially what we're left with is direction. Unfortunately, when we move outside of Tor, applying machine learning techniques in an easy way, or a rapid sort of standard way, to network traffic that isn't all the same size and the same protocol, and essentially these cells, is not nearly as simple, right? So we have some inspiration. We want to basically end up at a way where we can supply machine learning classifiers with a standard representation, such as like an image of a packet. And we have some related work, but now we need to know how we actually get there, right? So what we've done is we've tried and developed some different standard representations for network packets. And along the way, we've sort of formalized these requirements for any sort of standard packet data representation that will be used like an image across a variety of traffic analysis problems. So I'm going to go through them all, and so we'll go through each one individually. So first, we want any standard data representation for a packet to be complete. And completeness is this idea that each feature or every bit of every packet can be represented to the classifier. And this means that every field for each packet needs to be able to be included in a standard data representation. So below we see we have two packets, right? We have a TCP packet and a UDP packet. And the hard part is, right, when we have two images, they're just a bunch of pixels. Unfortunately, here we have two packets that actually contain different information entirely. One of them has UDP header and one of them has a TCP header. So we want to be able to include both of these packets, be able to represent both of these packets that contain different information with one representation, one standard representation. And our intuition is that if we have a standard representation, that the models can actually determine which features are important or which parts of the packet are important for a given problem without all this human guidance that's been used before. Okay, so first we want to be able to represent each feature for every packet. The second requirement that we landed on was that we want any standard representation to be constant size per problem. And what this means is that the size of the representation is the same for each packet. And for images, right, we can just scale an image and the pixels still mean the same thing. We just lose resolution. Unfortunately, scaling doesn't really work for packets. The real pain is the fact that different packet headers, right, like an IP header or TCP header, are variable length. And then we also have different size payloads. So we actually have packets that are different lengths entirely that we need to be able to represent in a constant size. And the real reason that this constant size requirement comes up is that for the majority of machine learning techniques that we're going to use, they actually only take constant size input. So there are some machine learning techniques that can take variable length input, but the vast majority of them, we're going to need a constant size representation to be able to have some sort of standardization in this area. So what is an example of something that meets some of these requirements? So the classic way we started was, okay, we can use our semantic understanding of packets to build a standard representation. And so this semantic view involves packets being broken into headers, and then each header is broken into fields, right? So we have a packet, and then we have the IP header, and then we have the TCP header, and then those are broken up even further into fields like the source port and the version. And we can actually encode each header field. So the TCP source port is just encoded as itself, and the IP version encoded as itself. So the TCP source port would be 80 in this instance, and the IP version would be 4, and represent that to a classifier. And this is going to be constant size, right? We can just extract every feature, every field of every packet header that we know of, and represent them all to a classifier. Unfortunately, this doesn't quite get what we want. And the reason is because when we think about packets semantically and representing them to a classifier in a standard way, we actually lose a lot of information and have trouble with certain parts of the packet. So the first problem is that we actually lose the ordering of TCP options. And not just TCP option, any really unstructured part of the packet. So TCP options have been widely known and used to differentiate operating systems, device characteristics. They're widely used at Nmap as a very predictive feature for what device is behind traffic. And when you encode in a semantic way, you lose this ordering that has so much information about what device generated the traffic or so on. Another problem is that when we represent packets in a semantic structure, if we don't actually know the semantic structure, we run into a lot of problems. So like when we have unstructured parts of the packet, like the payload, we can't just represent them numerically with their byte values because there's no real meaning. The third problem is that machine learning techniques work really well with normalized data or standardized data. And we want every feature to sort of lie between a standard range of values, say -1 and 1. And what this does is it allows a classifier to be more stable in terms of training faster and have more stable predictions. And with network traffic data sets, they grow so large so quickly that if we have to normalize each specific feature, so say we need to normalize the source port between 0 and 1, we actually need to know the range of those values. And this is incredibly expensive computationally and in terms of holding the values in memory. So we actually need to encode this as a formal requirement, this normalization technique. So we're going to encode a third requirement into our formal requirements that we would like a standard data representation to be inherently normalized. What does inherently normalized mean? It generally means that naturally, when we transform every packet, each feature ranges between -1 and 1. So we don't have the source port having a wildly different range of values between 0 and 65,000 versus the version between 0 and like 16, right? And if it's inherently normalized, this also allows, beyond just stabilization, it enables not having these computational passes to normalize the data, which when you're running traffic at the speeds we have today, you just don't have time to actually normalize these data sets in a streaming capacity, at least. So how can we actually come up with something that's inherently normalized and complete, right? So let's turn the classic semantic view of packets on its head. Let's think of packets as just a collection of bits, right? So this is naturally complete. We see below, we have a TCP/IP packet with a semantic representation and then this naive binary representation of a collection of bit strings. It's pretty easy to see that it's now complete, right? And it encodes ordering as well. It's pretty obvious that each bit can be represented as itself. And then we also have this bonus guarantee that when we consider every packet as a bit string, it's inherently normalized. So each feature is naturally going to range from -1 to 1, really 0 to 1, because we're using the bits themselves rather than their semantic encoding of those bits to represent to the classifier. So unfortunately, this doesn't really get us there either, right? So because packets have different variable links, and even headers inside of packets have variable links, we can run into this problem where we can actually have a problem with our encoding where different bits or features, when we represent them to the classifier, will have different meanings. So below we have a TCP packet that has IP options and TCP options, and then we have a TCP packet with no options at all. And what we see is that when we represent this to a classifier, the first TCP bit and the first IP options bit, we're actually presenting them to the classifier as the same feature. And this is going to directly inject noise into our classifier when it's trying to learn and confuse it. So we're actually going to penalize or decrease our overall performance by considering the fact that each bit is a feature, right? So this problem only becomes worse when we have different types of packets. So to illustrate this more, now we have two packets that we saw before, and then we have a UDP packet. And now when we go to represent this to a classifier, the first TCP bit, the first UDP bit, and the first IP options bit were presented to the classifier as, here's a feature. But what we've accidentally done is told the classifier that these are all supposed to have the same meaning, but we've actually just represented three different parts of a packet that have completely different meaning underlying it. And this cascades down the packet for a standard representation. So how do we avoid this? We have come up with a formal requirement to avoid this, this sort of misalignment. And that requirement is aligned. Any standard data representation for a packet, when we do this, needs to be aligned. And this is the idea that every location in the representation needs to have the same meaning across all packets. This is going to do two things. This is going to re-encode the semantic structure that we know packets have, that we've know that those bits have this meaning. And it's going to allow us, after we train a model on this representation, to actually interpret the model and figure out which parts of the packet actually differentiate different classes. So for example, this will allow us to take a trained model for like active device fingerprinting in the Nmap case. And it will allow us to determine, okay, the TTL actually is the important part that's driving the classifier's performance and distinguishing these classes from each other. And we'll see that later when we can actually interpret these models. Okay, so this is where we've landed. This is nPrint. It meets all of our requirements. So first, it's complete, and then we can represent every single bit of the packet to the classifier of any packet, because we include room for every protocol that we're interested in for a given problem. It's constant size in the sense that by padding to the maximum size of a given header, we are able to guarantee that the classifier gets constant size input. It's inherently normalized, and the way it's inherently normalized is, once again, we're using bits. And we're going to fill any feature that doesn't exist. So for example, in a TCP packet, we're going to fill the UDP bits with -1 to denote to the classifier that those bits did not exist in the packet. And now it's aligned, right? So by including room for the maximum size of each header for each protocol, so we see the IPv4 header is padded to the maximum size of 60 bytes, and so is the TCP header. Now, all of a sudden, when we have two packets that are actually completely different packets, right? We have a TCP packet and a UDP packet. We actually don't have this misalignment because we're encoding to the classifier in the representation itself that these are different packets, and we don't have this noise injected that was done with the naive version of nPrint. So we built this standard data representation that can encode any packet in a relatively efficient way and in a standard way. How do we actually use something like this? So we removed this hand engineering features step we see. So now we see that the bulk of the time is spent training models, right? So can we remove this step? So the classic methodology for training a model, including what we've done in the past on different works, is we'll do the following. We'll pick our favorite model. We'll write code to search some hyperparameters for that model. So say we want to use a deep neural network, the hyperparameters may be the size of each layer. And then we'll choose the best one in our search space, right? And what this is going to do is it gives us a relatively small search space with our bias of our favorite models. And hopefully we find a model that does a good job of predictive performance. But what is more principled is this new research area of automated machine learning, or AutoML. And what AutoML is it's going to automate and more efficiently do everything we've done before over a wider range of wider search space. And the way it does it at a high level is it's going to set up the machine learning. It's going to set up the model selection. So it's going to search for different models and different hyperparameters as an actual optimization problem rather than a simple search space. And this is going to guarantee better performing models than picking and injecting human bias into our model search. So specifically, we're going to use AutoGluon AutoML. So what AutoGluon is it allows us to basically take a CSV file and run optimized machine learning tests without writing any code. And AutoGluon is built by Amazon, and it's been shown to achieve higher performance than other models due to ensembling models, or basically just combining different models to mask their other one's weaknesses. And this is going to allow us to train and test over 50 models from 6 different base model classes for every single problem we test without actually writing any code. And so this is what our ultimate pipeline looks like. So typically you would do this all individually for every single problem. But now, right, we take input as packets, we run nPrint on those packets, and then we run AutoML. And as opposed to all this time spent figuring out which features are important and figuring out which models are important, this entire process becomes automated. So we're going to go through 2 quick examples of applying nPrint and how it can actually outperform state-of-the-art tools in its areas. So first, we need labels, right? So if we want to perform a classification task, we need some sort of labels to actually classify. First thing we're going to look at is classifying a set of network devices and IoT devices. These are gathered through a variety of means. Basically, it's a lot of routers and then some IoT cameras and IoT streaming devices. So we have labels. Now we need packets to actually transform into nPrint and classify. So we're going to leverage Nmap, which is the most well-known and used remote device fingerprinting tool, probably. It's really, I think it's over 20 years at this point of, hand-curated features and fingerprints and this heuristic to actually fingerprint remote devices from traffic sent from your device. So how does Nmap work? At a high level, it's going to send a bunch of probes, 16 in total. It's going to take the responses to those probes and transform them into a fingerprint using a bunch of tests. And then it's going to compare that fingerprint to a database. And if it finds the fingerprint or something close to it, it's going to say, okay, this device is probably, a Cisco router, for example. So what we're going to do is we're actually just going to take the responses to Nmap's probes they spent a long time developing, and we're going to compare if nPrint, models trained on nPrint can actually just automatically do the second part of transforming the responses into something useful without actually doing all the work for the past, decade or more. So now we need to actually transform the packets or the responses to the Nmap probes into something we can use. And we're going to run nPrint, and then we're going to compare it to Nmap. So how does this look like for nPrint? So Nmap sends a bunch of probes, and it gets 21 responses in our data set for each device. So we can now create our own fingerprint picture, like I talked about at the beginning, where we have a set of pixels. Now we've sort of created our own device fingerprint that is a set of carefully aligned and carefully set up pixels that we can represent to a machine learning classifier. And so ultimately, this is going to look like a flattened version of the 2D sort of image to the right. So essentially what we have is for each device, we now have a fingerprint image in terms of its network traffic. What does Nmap do? It transforms the packets into a variety of features, some complex, some simple. So some just looking at the length of the packet. And then we also have things like the predictability index that are actually relatively complex. So we're going to take the imprints of the same responses that Nmap transforms and Nmap's test fingerprint that it generates. And we're going to train a bunch of models using automated machine learning on Nmap's features and imprints. So we're going to see if nPrint can actually uncover the important features without actually extracting them by hand that took so long to develop. So on the left, we see a precision recall curve. In general, up and to the right is better. So we see that nPrint actually outperforms Nmap in terms of precision and recall for every class. On the right, we have a small table. These are standard metrics, including accuracy and F1 score. And we see almost a 3% increase. So what does this mean? At a high level, what we're seeing is that models can actually automatically extract important features from packets without actual human guidance and outperform features that have been developed by human guidance for a long time. Earlier, I talked about interpretable features because of nPrint. So nPrint is unique in that it's interpretable at the bit level, right? So we can now probe our model and determine by its feature importance what it learned to distinguish the classes of routers or network devices and IoT devices. So we actually see that it actually automatically learns features that are already encoded into Nmap, for example. It learns that the IPTTL is incredibly important. It learns that the window size is incredibly important. It finds value in the ICMP header that gets responded to by the Nmap probe. And we're actually able to automatically do this and find out after the fact rather than having to extract it ourselves. So last, we're going to look at application identification. This is very brief, just to show the breadth of nPrint. So the data set for application identification, there was a collection of 7,000 DTLS handshakes. This was an effort to identify Snowflake, which is a new pluggable transport and tour. The author of this was actually able to extract manually a bunch of features that lead to 99% accuracy to determine the application that was in the handshake. So what we're going to do is we're going to say, okay, rather than manually extracting features, let's see if we can actually just run nPrint on the handshakes, train models on the raw nPrints that we generated, and see if we can match that performance without any effort at all. So what we find on the left is that with 99.9% F1 score and 99.9% accuracy overall, nPrint is able to adapt to this environment and extract different features for a new problem without any effort. This actually took 0 lines of code to train a new model and learn new features. On the right, we see that it learns different things, like the length of each handshake is actually important in terms of the total length of each packet, and then the DTLS header itself has a lot of importance. I think that's it for me. Thank you guys so much for your attention and having me, and now I'll take any questions.
Jordan, thank you very much. That was amazingly informative. We just have a couple of minutes for Q&A. I've been reading the ones you've already answered in the Q&A tab. I'd like to pull out 2 questions in specific for you.
Yeah.
First question, is there any issue or additional overhead introduced when handling jumbo frames versus standard frames?
Yeah, ultimately, with our approach, the larger the packet is, including the payload, the more overhead and the number of features you're going to have. So ultimately, yes, the bigger the packet, the bigger the overhead for the classifier. We're working on ways to reduce this in terms of compression of the traffic itself and training on compressed versions of it.
Cool. The other question, which you haven't answered in the chat, and everybody should go look at the chat, why wouldn't you have a field that says TCP, UDP, ICMP, and then put everything to a single 480 feature field called header, padding the smaller 2 with zeros out to 480?
Yeah, this is a really good question. Ultimately, with the classifier, we want to encode one piece of information in every feature we present to the classifier to learn from. And we'd be putting extra strain on the classifier itself. A, by having to figure out that these are actually different packets. And B, we're actually, by doing that, we'd be encoding both like the TCP window size and the UDP checksum, for example, in the same feature, which would ultimately end up with confusion in the classifier at lower performance. That's a really good question.
Cool. Thank you. Those were the last of the questions. I learned a whole lot about that, and I think I'll be diving into it, or actually having one of my guys who actually understands coding at that level dive into it. Thank you very much.